What's up, geometry? Thanks for tuning in for another episode of Math with Mullins. Today we're going to be looking at our our semester 1 exam review, day 2. So this is part 2 of your semester exam review. So let's go ahead and get started. We're starting with number 19. We want an equation of the line that's parallel, meaning same slope. And we're going to have to use these points, 6, 2. I'm going to use point slope form. So y minus y1 would be y2 is equal to 1/3. That represents your m, or your slope, parentheses x minus x1, or x minus 6. I'm going to go and distribute my second portion of this. So this is 1/3 x, and then 1/3 times 6 would be 6/3, which is equal to 2, so minus 2. Then I'm going to add 2 to both sides. I'm going to get y is equal to 1/3 x. Okay. Next up, we have a perpendicular slope. So that means we have to do opposite reciprocal. So when we set this up, we're still going to do y minus y1, so y minus 3, but now instead of 2/5, we're going to do negative 5/2, and then parentheses x minus x1, x minus 3. When we distribute here, we're technically doing negative 5/2 times x, but then we're doing negative 5/2 times negative 3/1. That's going to give us 15/2. So you can keep it as 15/2. It's going to be positive because a negative times a negative is a positive. Or if you change that to 7.5, that's fine. I would change this to 7.5 because in the end, we're going to have to end up adding that 3x, and I find it easier to add with decimals than fractions. So I'm going to add 3 to both sides. And we should get y is equal to negative 5/2 x plus 10.5. Okay. For number 20. 21, another perpendicular question. Be careful with this one. Another way to see this line, y is equal to 1/3 x minus 2. So the slope would need to be negative 3/1 or just negative 3. So that's me flipping the making the reciprocal, making it opposites. So I'm going to do y minus y1, y minus 2 is equal to negative 3, parentheses x minus x1, or x minus 6. When we go ahead and distribute this, we're going to get negative 3x plus 18, and then add 2 to both sides. We're going to get y is equal to negative 3x plus 20. Okay. 22, use a figure to list 2 examples of pairs of lines that fit the description. These can have a lot of examples, so I'm just going to list them all. You only needed to just list 2. So I'm going to start with KN is parallel to ML. Okay. You can do RQ is parallel to SP. You can also do the front and the back. So like KL is parallel to NM. And you can also do RS is parallel to QP. Okay, so those are all the options for parallel lines. Perpendicular just needs to be making that 90-degree angle. So I can say like NQ, perpendicular symbol to QP. Notice how I'm just going to continue using one letter at a time. So I can say PQ is perpendicular to PS. Okay, and then maybe one more from the top. I'm going to say LK is perpendicular to LM, etc. Okay. Skew lines cannot be parallel or perpendicular. They're not going to intersect, and they're in fact going to be on 2 different planes. So you can say like NQ and RS, or you can say QP and NK. So just as long as you're choosing not parallel or perpendicular lines, you'll get those right. The next part we're going to talk about is a dilation. The definition of a dilation is what you're supposed to put here. So that just is going to change the size, but not the shape. Okay, so it's still going to be kind of like similar figures when we do a dilation. Okay, so if k is equal to the scale factor, the enlargement will happen when k is greater than 1. A reduction will happen when k is less than 1. And a dilation in the coordinate plane, you're going to multiply the coordinate points by the scale factor. So if it was 1/2, you'd multiply everything by 1/2, or if it's 2, you multiply everything by 2. What happens when the scale factor is negative? It's not only going to dilate it, but it'll dilate and rotate 180 degrees, okay? And we might see a few of those examples coming up. 23, these vertices we're going to translate. So what I'm going to do first is put down all the original points, and then we'll show the translation. All right, so the first thing we want to do is write down where original points are, and then we're going to use the vector 5, -3. This just means I'm going to go right and then down. So you would take each one of your points. We can start maybe letter E, 1, 2, 3, 4, 5, down, 1, 2, 3. So E prime would end up down here. Okay, E prime now is at 11, -2. We're also going to write those new coordinates. Point D to the right, 1, 2, 3, 4, 5, down 1, 2, 3. D prime is now looking like it is at 9, 6. And then C to the right, 1, 2, 3, 4, 5, down 1, 2, 3, right there on the x-axis of 2, 0. And then you just connect your points. Same shape, same size. We've just moved to the right and down. The next one, we're going to take this image and reflect it over the x is equal to 5 line. So let's go ahead and put all of our original points down first. So here is BCD, -1, 1, 2, 4, and 5, 2. Now what we need to do is we need to find the x is equal to 5 line. So I'm going to highlight that in orange, and D is actually on that line of reflection. So D would not be moving. So D prime's letter or number would still be the same, 5, 2. C prime is here at right here. We are 1, 2, 3 steps away from the line of reflection. So move 1, 2, 3 steps on the other side. C prime is now at 8, 4. And then D prime still there, but B prime is 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 for B prime. That's 11, 1. I'm going to go ahead and label D prime there as well. Connecting my points, mirror image over x is equal to 5. This next one says, does this figure have lines of symmetry or rotational symmetry and or rotational symmetry? And if so, describe it. Right now I am seeing 6 lines of symmetry. So let's talk about lines of symmetry first. 1, 2, 3, and then 4, 5, 6. So 6 lines of symmetry. Okay. And one thing we can talk about for rotational symmetry is when you rotate this figure, it has to be 180 degrees or less. Okay. I know that for the rotational symmetry, I can do 180 degrees rotation just because that'd be flipping it upside down. But another thing I could do is maybe think about how many sides there are and then use that to determine how many degrees I would have. So your rotational symmetry could also happen at 2 other places. You want to think about it this way. Since this figure has 6 sides, that means every 60 degrees, you're going to have rotational symmetry. So you could start at a 60-degree rotation, 120 would end up being next, and then the third one would be 180. Okay. The next one we're going to do is graph a line called ST, and then we're going to rotate it 90 degrees counterclockwise about the origin. So ST is going to start off being at -3, 0. So here's S, and here is T. Okay. Now, when you do 90-degree counterclockwise, what's going to happen is you're going to trade places with your X and Y. So say, for instance, and we talked about this with A's and B's. A and B will switch places, and B will become a negative, okay? So like S prime would switch places, a 0 would be in front, 3 would be in the negative, 3 would be in back, and the 0 changes to a negative, which we really don't do that because 0 can't be changing to negative. So 0, negative 3 is where that one would end up. And then T, if we switch those around, negative 1 would come in the front, positive 1 would go in the back, and we would change negative 1 to a positive 1. So T prime would then be at positive 1, comma 1. So if we reflect that 90 degrees counterclockwise, that just means from where T is right now to its new point T, I'm making a 90-degree turn in the opposite direction that a clock runs, which is why I'm going to get here at positive 1, comma 1. 0, negative 3 would end up over here to, or not over here to the left, but down 3. So here's S prime, and here is T prime. And then we just connect our points, okay? Graphing XYZ, and we're going to dilate by a scale factor of 1/2. The first thing we're going to do is go ahead and graph the original points. Here's our original points. Then the next thing I do is always find it's easiest to go ahead and change these points before dilating. So X prime, if I multiply that by 1/2, is going to be 1, comma 2. You're just cutting everything in half. Negative 2, comma 1. Negative 1 will be negative 1, comma negative 0.5. And then Z prime would be 2, comma 0.5. Okay? So when we graph these, over 1 up 2, here's X prime. Y prime is negative 1, negative 0.5 here. Z prime is 2, positive 5. Still the same triangle, we just shrunk it down so they're both similar figures. Okay? 28. Almost done. We got a few more, and then we're going to look at some proofs. Describe the congruence transformation that maps VJK to RDI. So typically what I like to do first is I like to see if it's a translation and a reflection. So it looks like I'm going to go up 1, 2. So I went up 2. And then if I count to the y-axis, 1, 2, 3, 4, I'm also 1, 2, 3, 4 away. So I went up 2, so this would be x comma y, x, and then y plus 2. And then I reflected over the y-axis, okay? If you switch this around, it could be vice versa. Reflect over the y-axis, then translate up to, okay? You can say translate up to, or just give me the rule that we wrote here. Either one would work. 29, find the scale factor of the dilation. Remember, for finding scale factor, we just say no. That means new over the original. The new one looks like it's P prime, and that is 12. The old one looks like it's 8. So I'm just going to reduce 12 and 8. I'm going to divide both those by 4, and I'm going to get 3 over 2. Since this is 3 over 2, this is going to be considered an enlargement. Okay? All right, now come the proofs. So let's go ahead and talk about proving the following things. We have our statements and reasons. Always want to start off with what we're given. P is parallel to Q, cool, and angle 1 is congruent to angle 2. What we're going to try to do is also prove that L is parallel to M. Something we can say here is maybe moving forward, you can maybe start with angle 1 is congruent to angle 3 because of the alternate interior angles theorem. You can also say that angle 3 is congruent to angle 2 either by another alternate interior angles theorem, or you could even say transitive property or substitution. And because you've now shown that you've got some equivalent angles that are also connected to the L and the M line, you can now say, a number of those, L is parallel to M using the AIA converse theorem, which just states you have two equal angles that are alternate interiors, then they would prove those lines are parallel. In order to prove those lines are parallel, you have to use converse theorem, If you were trying to prove angles, then you would just use alternate interior for that proof. And next up, we have this one. A is parallel to B. We know the measure of angle 5 plus the measure of angle 2 is 180, so we want to prove that L is parallel to M. So kind of along the same lines we just saw with the first one, except now we have maybe a few more steps. So let's start with our first statement, our givens. A is parallel to B, and the measure of angle 5 plus the measure of angle 2 equals 180. Okay. Because of that, angle 2 and angle 5, you also maybe want to maybe pull in angle 1 here because we haven't discussed angle 1 yet. So let's talk about angle 5 can be congruent to angle 1 because they are, you can say, either corresponding angles okay. So because 5 is equal to 1, that means we can say the measure of angle 1 plus the measure of angle 2 is equal to 180. This one, there are two different reasons you can say. You can say consecutive angles or supplementary. Okay. Then, because we have these written here, you can now prove that L is parallel to M using the consecutive interior angles converse. Okay. And then our final proof of our review, we know that HGJ is equal to 90 and the measure of angle 3 is equal to 90. So how can we prove angle 1 and 2 are also equal to the measure of angle 3? So let's start with our statements and reasonings with our givens first. The measure of angle HGJ equals 90 and the measure of angle 3 also equals 90. Okay. What I would start looking at is if these are obviously on a straight line. So what I maybe you could even say that HGJ is also equal to 90 because we're just substituting what we're given here. So the measure of HGJ is equal to the measure of angle 3. I would even say maybe that's either substitution. If you created one more step in between here, you could have also done the transitive route. Okay. Once we have that, then we can say the measure of angle 1 plus the measure of angle 2 is equal to HGJ, because that's shown in the diagram, or the angle addition postulate. So now you can wrap it up and say the measure of angle 1 plus the measure of angle 2 equals the measure of angle 3 using the transitive property. Okay, that'll conclude our